All right, thanks for coming to my talk. My name is Brian O'Malley. I'm with the USGS based out of Oswego, New York. Today I'm going to talk to you about a project that's kind of stemmed out of a funded project we had back in 2018. And the title of this talk is Quantifying Benthic-Pelagic Flux of Mysis biomass through diel vertical migration on a lake-wide scale. I'd like to acknowledge co-authors on this, Georgie Hoffman, who's also with me at USGS in Oswego. Also Rosie Shapina and Jason Stockwell from the University of Vermont, and Lars Rudstam from Cornell Biological Field Station. So for those of you not familiar with what Lake Ontario looks like and the depth gradients, this is a map of that. So it's kind of what I like to think of as a bathtub-shaped lake. There's kind of two sort of distinct deep areas of the lake, just to orient you a little bit with that. So, it's mostly been fish talks today. So what are mysis? They're this macroinvertebrate, about the size of your thumbnail or so when they're adults. And they're just really pretty remarkable organism in terms of their migration behavior. So in the Great Lakes and throughout North America, there's mainly one species, Mysis diluviana, and it's known to sort of couple benthic and pelagic habitats because they feed in both areas. When they migrate up to about 20 or 60 meters below the surface, they access phyto and zooplankton, and then during the day generally migrate back down and have access to feed on detritus and benthic invertebrates. They prefer generally cold water, less than 12 degrees Celsius, and they're very, very scared of light. If you bring them up into the daylight like this, it can kind of basically blind their eyes. So a sort of conceptual model of how they're distributed throughout the day in lakes. Like I said, so during the day, at shallower zones, they're kind of excluded from really shallow zones because the water is too warm for them and too bright. But in general, during the day, at sort of intermediate depths, we think that they go all the way down to the bottom, but we also have some evidence to suggest that they can sort of suspend and be off the bottom in deeper pelagic areas. And to contrast that with at night, we have pretty good evidence that they all seem to sort of move up and form this, what we call a mysit layer, sort of beneath the thermocline. There's another part of this that I'm not touching upon, but we also think there's this benthic component that might stay behind, so we've called that partial migration. But for the focus of this talk, I'm just going to be focusing on their pelagic movements and really trying to understand what's the connection here between the amount that suspends during the day to the amount we see in the water column at night. So throughout the Great Lakes and elsewhere, there's been a lot of surveys conducted at night. This is how we typically assess their populations. This is a graph or a map of Lake Ontario from a 1974 study. Each point here is a different sampling location where the vessel went and sampled mysis. And when I first looked at this, I was like, wow, that's pretty amazing that they were able to accomplish all that. And this was a 5-lake study, so they went all throughout the Great Lakes doing this. And I thought, man, that's just crazy. So I was like, how could they sample all these stations at night? And then I was reading the methods, and I was like, oh, okay, so they actually sampled these different stations regardless of time of day. And they put this quote here saying that they noticed there's no variation in the abundance attributable to differences in time of sampling. So I thought, well, that's interesting, because we talk about, at least at these shallow sites, that they're going to be all the way down towards the bottom during the day. So why would you sample day and night without accounting for that? And so that kind of led me into the graph from my graduate work at Lake Champlain, where we went out and sampled at a 100-meter station, just sampling in the water column day and night. And sure enough, I thought for sure it wasn't going to look like this. I thought I was going to see much bigger black bars and then small bars during the day. But I was like, okay, so Carpenter was onto something there. Just offshore sites, it seems to be about similar. So thinking about this more, I was like, okay, well, we always talk about them as benthic-pelagic couplers, but that doesn't seem to be the case if we're seeing similar abundances day and night in the water column. So, the question I had going into this talk was, is there a way that we can quantify benthic-pelagic movements with mysis? And, I mentioned they're about the size of your thumbnail, so it's kind of a tricky organism to work with. You can think about maybe putting tags on something, quantifying the behavior, but it's, to the best of my knowledge, it's not really feasible with something like this, an organism like this. There's also, you could maybe use acoustic samplers to sort of quantify how much are in the water column during the day and night. But we have some challenges with sampling the benthic zone. You could also use nets and sleds. A benthic sled towed horizontally along the bottom, you could estimate how many are there. but it's kind of difficult. So it's much easier to just sample the ones in the water column. And like I said, you can know something, at least at the shallow sites. It's pretty easy to conclude if they're absent during the day, present at night, then you can assume that basically 100% of the Mysis you're observing at night in the water column came from the bottom. So thinking about how to sort of set up a study in a lake that has depth gradients where we know that Mysis are going to be down on the bottom versus some of these deep offshore areas, I just sort of wanted to try a very simple calculation by using a paired sampling design, sampling at the same location day and night along a depth gradient. And so I came up with this sort of formula, just taking the biomass we observe at night minus the biomass observed during the day, again at the same site, divided by that amount at night, to sort of estimate the portion that comes from the lake bottom. And this is just a schematic. It's kind of with some predictions right now, just thrown on there, but I'll break it up into sort of three different groups or categories of their vertical migration behavior, again, looking at the population at that site. So values that fall out towards this, a value of 1, this would be an area where they're absent during the day, present at night. So this seems like a classic benthic-pelagic DBM by that organism, or by that population at that site. As you move down the y-axis here, values between 1 and 0, it's some sort of about a mixed population. The extent, varies where you are on that scale. But some, so you're getting some individuals during the day, but you're getting more at night. So suggesting that some are benthic-pelagic and some might be just moving from deep pelagic layers to shallow pelagic layers. And of course, then there's the third option where if you're getting the portion here of 0, where you're getting basically equal amounts day and night, then that's really not probably a benthic-pelagic movement. It sounds like it's more suggestive of something that's just migrating within the pelagic habitat itself. So we went out to sort of test this in Lake Ontario. Like I said, we had a paired sampling design. So each point here, the triangles are the amount we observed at night in the water column. I should mention these are from whole water column tows with plankton nets, large diameter plankton nets, and we just said anywhere from 2 meters off the bottom because we don't want to drop the net right on the bottom and disturb any of those animals or fill it up with mud. Towed all the way up to the surface, and then we counted everything in the sample. So we had a density estimate, and then we converted that to biomass by using a length-weight regression. But so each point along the x-axis here is one of those sites. And so, for example, at this site, about 60 or 70 meters, you can see we got 0 during the day and slightly more at night. And it wasn't until during the day, once you got past about 150 meters or so in Lake Ontario, that we started seeing really substantial amounts during the day. And these points here, out towards our deepest site that we had sampled, 200 meters, you can see there's a lot of overlap between the different points. My one regret with the study design so far is that we didn't go out to 240 meters, which is like the deepest part of Lake Ontario. If I were to do it again, I'd go just a little bit further so I can extend the graph here, but I expect it to not be much different past 200. And that's why we kind of stopped there. So using these data, and each point I should also point out is the average of multiple replicates. It's not just a single toe. There's a lot of